Let's go on and talk about our next topic that we're going to have in our new unit, which is electrochemical reactions. And so, what we're going to get to as we get through this chapter, which is chapter 20, is talk about how to construct electrochemical cells and voltage potentials and stuff like that. But we're starting just kind of back where we left off in chapter 4 with oxidation reduction reactions or redox reactions. And so this first half of this video is just going to be a review for you. And so electrical chemical reactions is simply just another name for redox reactions in which we're transferring electrons from one species to another. And so we use oxidation numbers to keep track of that. And so here's an example of a redox reaction in which zinc, and if you remember from the table, the activity series of metals, zinc is higher on the activity series than hydrogen, so it can displace hydrogen. And so here zinc is being oxidized from 0 plus 2, hydrogen is being reduced from plus 1 to 0. What happens here is that if you just put a piece of zinc into a hydrochloric acid solution, you'll get hydrogen gas bubbling out along with zinc chloride. But the chloride is a spectator, and so spectators tend to be left out of these redox reactions. So just as a reminder, oxidation is lost. So zinc is being oxidized here because it's losing 2 electrons to go from zinc 0 to zinc plus 2. Hydrogen is being reduced here because it's gaining 1 electron to go from hydrogen plus 1 to hydrogen 0. And so just let's remind ourselves what some of the rules are for assigning oxidation numbers. And this is review from chapter 4, so I'll go through it rather quickly. And remember that these rules are hierarchical. That is, that we apply rule 1 before we apply rule 2, and rule 2 before rule 3, etc. And so just as a reminder, the first 2 rules are that elements in their elemental form have oxidation numbers equal to 0, and the oxidation number of a monatomic ion is the same as its charge. And you'll notice that those two rules actually will allow us to balance this, assign oxidation numbers to this whole equation, because we have zinc over here and hydrogen gas over here in their elemental states, and so their oxidation numbers are equal to 0. And then we have zinc ions here and hydrogen ions here, and so their oxidation numbers are equal to their charges, in this case plus 1, in that case plus 2. The next thing we do is to balance the assign oxidation numbers to nonmetals, and the 2 ones that we can generally assign oxidation numbers to very quickly in compounds are oxygen and hydrogen. So oxygen is essentially always, for the purpose of this course, going to have an oxidation number of -2 in compounds. And hydrogen is almost always going to have in compounds is almost always going to have an oxidation number of +1, unless it was bonded to a metal, in which case it was -1, but that is rather rare. And then you're usually left with some other species that you have to balance, and you simply balance those algebraically using these 2 principles, that if we have a neutral compound, the sum of all the oxidation numbers in that neutral compound has to be 0. And if we have a polyatomic ion, then the sum of all the oxidation numbers in that polyatomic ion has got to be equal to the charge on the ion. Now, when it comes to balancing oxidation and reduction equations, it's a little bit more complex than balancing the chemical reactions as we've learned in chapters so far. And that's because it's not just enough to balance the atoms on both sides. These things typically appear as net ionic equations rather than showing all of the atoms in the compound. And so it's important to not only balance the atoms on both sides. So here's an example. If I oxidize zinc with silver, it's zinc plus silver 1 gives me zinc 2 plus silver 0. You'll notice that this thing is balanced on both sides with respect to atoms. There's 1 zinc on each side, and there's 1 silver on each side. But the charges aren't balanced. The total charge on the left-hand side is +1, and the total charge on the right-hand side is +2, which essentially means I've made an electron disappear in the process of doing this. And that's not allowed to occur because an electron is in fact matter and you can't make matter appear or disappear. What you have to do is balance it for charges as well. And so it's fairly simple with this equation. I just multiply the silver by 2. Now I've got 1 zinc on both sides, 2 silvers on both sides. I've got a total charge of +2 on the left, and a total charge of +2 on the right. So things like this one are fairly easy to do just by inspection, but you'll get more complicated redox equations that you have to balance, and they're not as easy to do. And so there are a couple systematic ways to do this. One is what your book teaches you, which is called the half reaction method. And so we're going to go through this in just a moment. It takes longer than the other method I'm going to show you, but it doesn't require you to be able to assign oxidation numbers to anything. And that's something that people still have some struggle with or just don't really feel a lot of confidence in. Then there's another method in which you do use oxidation numbers, and that takes less time to balance a redox equation, but you have to be good and feel confident in your ability to assign oxidation numbers. So let's take a look at the half reaction method first. This is going to essentially treating on paper the oxidation and reduction as occurring in 2 separate processes. So splitting a reaction up into its half reactions, balancing each of those half reactions separately, and then combining them back to get the balanced equation for the overall reaction. So here is just a walk through the steps of this. The first step is actually one that I think you can ignore, which has to do with assigning oxidation numbers, because you really don't need to assign oxidation numbers to anything to use this method. But then you're going to split the redox reaction into its 2 half reactions, and I'll show you in a moment how that's done. Once you've split it into its half reactions, you're going to balance each half reaction first by balancing anything in the reaction that is not a hydrogen or an oxygen. Then balancing the oxygens by adding water molecules to whichever side has fewer oxygens. Then balance the hydrogens by adding hydrogen ions to whichever side has fewer hydrogens. Then balancing any difference in charge between the 2 sides of the equation by adding as many electrons as are necessary to whichever side has a more positive charge. Once we've done that, we need to multiply each half reaction by some integer value so that the number of electrons on both sides is the same. And then we add them together and make sure that anything that appears on both sides gets subtracted out. And then we do a final check. So let's go through an example. And the example we're going to look at is actually from a lab experiment that we may do at some point, but this is a typical AP chemistry style lab experiment, which is a redox titration in which you're adding permanganate, which is purple, to a solution of the oxalate ion. And when they come in contact with each other, they react. And so the purple color of the permanganate goes away. And the way you know that the reaction is over is that the purple color of the permanganate now begins to persist. And so it's in that sense, it's like a phenolphthalein indicator in an acid-base reaction. But this is the equation, permanganate, which is MnO4 minus, plus oxalate, which is C2O4 2 minus, gives you manganese 2 ions and carbon dioxide. And so the first thing we want to do is split this into its half reactions. And how are we going to do that? Well, we're simply going to say, okay, I've got one species over here on this side that's got manganese and one that's got carbon, and another species on this side that's got manganese and one that's got carbon. And so we can divide them into a manganese half reaction and a carbon half reaction. And so let's start with the carbon half reaction first. The carbon half reaction is simply oxalate, C2O4 2 minus, going to CO2. And so C2O4 minus going to CO2, step 1 in that hierarchy was we're going to balance anything that's not oxygen or hydrogen. So carbon is the thing here that's not oxygen or hydrogen. I've got 2 on this side and 1 on this side, so I'm going to add a coefficient of 2 so that now I've got 2 carbons on both sides. The next thing to do is balance the oxygens, but I don't actually need to balance the oxygens because I've got 4 oxygens on each side, 4 here, and then 2 times 2 is 4 here, so I'm balanced on oxygens. There are no hydrogens in here, so I don't have to balance hydrogen. So the last thing I need to do is just balance the charges. This side has a net charge of -2. This side has a net charge of 0. The thing that I add to balance charges is electrons, and so I add them to the more positive side. So I add 2 electrons to this side. Now I've got a net charge of -2 over here and a net charge of -2 over here. Now let's take a look at the manganese half reaction. I am already balanced on manganese. There's 1 manganese on the left and there's 1 manganese on the right, so that's already balanced. I do need to balance oxygen. There are 4 oxygens on this side and none on this side, so I solved that by adding 4 waters to this side. That balances me on oxygen, but now I'm unbalanced on hydrogen. I've got 8 hydrogens over here and none over here, so I'm going to add 8 hydrogens. So now I'm balanced on hydrogen and manganese and oxygen, but I'm not balanced on charge because the total charge on this side is +7. This is +8 times +1 is +8, and I'm -1 is +7. The total charge on this side is +2. There's a difference of 5 electrons. This is +7, this is +2. I have to add 5 electrons to this left-hand side in order to get balance on charge. So now this is -5 plus 8 is +3, and a -1 is +2, and I'm +2 on this side. So now both half reactions have been fully balanced for charge and atoms. Now we look at the two of them together and say the last thing we need to do is multiply these things by integers so that I've got the same number of electrons on both sides. And so that means finding the least common multiple of 2 electrons and 5 electrons, which is going to be 10 electrons. And that means I have to multiply this equation by 5, and I have to multiply this half reaction by 2, so that I'll have 10 electrons in each case. And so when I do that, I've now multiplied through the top one by 5. I've multiplied through the bottom one by 2. And then I just add everything together. 10 electrons plus 16 hydrogens plus 2 permanganates plus 5 oxalates gives me 2 manganese 2s plus 8 waters plus 10 CO2s plus 10 electrons. Now I evaluate all of this to see, is there anything that appears on both sides? Well, in this case, it's only the electrons. And so I can cancel them out, subtract 10 electrons from both sides, and I'm left with my balanced equation. Now, it's always useful just to do a quick check to make sure you did it right. I got 16 hydrogens over here. I got 8 times 2 is 16 hydrogens over here. I've got 2 manganese over here. I got 2 manganese over here. I've got 5 times 2 is 10 carbons here. I've got 10 times 1 is 10 carbons there. I've got 8 plus 20, 28 oxygens. 8 plus 20, 28 oxygens. The total charge on this side is 5 times -2, -10, plus 2 more -1s makes -12. -12 plus a +16 gives me a +4, and 2 times +2 gives me a +4. So I'm fully balanced and I'm done. And so you were able to do that and balance that redox reaction completely for electrons and atoms and charges without having to assign an oxidation number to anything. But it took a while. Let me show you a different method that does require you to assign oxidation numbers, but it moves more quickly because you don't have to separate things into half reactions. So this is the oxidation of iodide with chromate to give you chromium-3 plus iodate. And so the first thing you have to do here actually is assign oxidation numbers. You don't need to worry about assigning oxidation numbers to oxygen because oxygen in compounds is -2. It's the chromium and the iodine that we're concerned with here. And so when we assign oxidation numbers, and I'm not going to go through in detail how I did this, you can pause the video and work these out yourself. But on this side, chromium is +6 and iodine is -1. On this side, chromium is +3 and iodine is +5. The next thing to do is see what's happening to each of these things. chromium is going from +6 to +3, so it is being reduced by a total of 3 electrons because it's going from +6 to +3. That's a 3 electron reduction. Iodine is going from -1 to +5, which means it's being oxidized, and it's being oxidized by a total of 6 electrons. That's a 6 electron oxidation. So I've got a 3 electron reduction and a 6 electron oxidation. And so I have to find the least common multiple of 3 and 6, and the least common multiple of 3 and 6 is 6. And so for the iodine, which is undergoing a 6 electron oxidation, I don't have to multiply that by anything. 6 times 1 is equal to 6. But for the chromium, which is undergoing a 3 electron reduction, I multiply that by 2 so that I have a total reduction of 6. And so that's what I'm going to do. I'm going to multiply the 2 chromium species by 2. And now 2 chromiums are being reduced from +6 to +3. That's a total of 6 electrons. 1 iodine is being oxidized from -1 to +5. That's a total of 6 electrons. So I'm now balanced on electrons. Now I just finish this out the same way I did balancing the half reactions for elements. I'm balanced on chromium, 2 chromiums, 2 chromiums. I'm balanced on iodine, 1 iodine, 1 iodine. I'm not balanced on oxygen. I've got 8 oxygens over here, and I've got 3 oxygens over here. I'm going to add 5 waters to the right-hand side so that I'm balanced on oxygen. Now I'm not balanced on hydrogen because I've got 10 hydrogens over here and none over here, so I'm going to add 10 hydrogen ions to the left-hand side. And now I should be done. So let's check. 10 hydrogens, 5 times 2 is 10 hydrogens. 2 chromiums, 2 chromiums, 1 iodine, 1 iodine. 2 times 4 is 8 oxygens. 3 plus 5 times 1 is 8 oxygens. And on charge, I'm a +10 here, and I'm a -4 plus -1 is -5. So +10 and a total of -5 gives me a total charge of +5 on the left. 2 times +3 is +6, plus a -1 is +5 on the right. So I'm balanced, and I have on atoms and charges. Well, I blitzed through all this quite quickly, and I would encourage you to go back and look through this video again, pausing in places where you don't understand. I've also am going to assign, or will have assigned, some practice problems for you to look at in the book to sort of help cement some of these principles. And the QOD will cover assigning oxidation numbers and balancing reactions.